Hi, Chris Kuzmal here. Today we're going to show that Herbrand logic is not compact, and this is in contrast to relational logic and propositional logic, which were compact. Compactness is a property of a logic which says that there is that no matter what set of logical sentences you have, if that set of logical sentences is unsatisfiable, then there is some subset that is finite that is also unsatisfiable. That seems pretty intuitive. Seems like you should always be able to pull out something that can't be satisfied if the whole thing's unsatisfied. But for Herbrand logic, we show that that's not the case. And the example that we have here is P of A and P of F of A and P of F of F of A and P of F of F of F of A and so on, which is actually turns out to be the elements of the Herbrand base for a vocabulary PAF. So actually the ground terms are technically A, F of A, F of F of A, and then we apply the relation to each of the ground terms. And that set of sentences, P of A and P of F of A and so on, entails for all X, P of X, okay? And so if we add in the sentence, there exists an X of not P of X, in other words, we're saying one of them is false. But if we've already said all of them are true and one of them is false, then that's the contradiction. One of them, this infinite set, is unsatisfiable. But our compactness says we should be able to find a subset of that infinite set that is also unsatisfiable. But every finite subset we claim is satisfiable because it's either missing that negation, in which case it's easily satisfiable, or it's missing one of the elements in the for all, and then we could just pick that as being the one where we have the negation and then flip the negation to be true by doing that as our truth assignment. And that will satisfy the logical sentence as well. So no matter what one thing we remove from our infinite set, we have a truth assignment that will cause the infinite set to be evaluated to true, and thus it's satisfiable. Okay, so let's look at it another way. We're saying the same thing a second time, slightly different type setting. Say for all X, P of X, and there exists an X not P of X. That again corresponds to P of A and P of A, and as well as P of loss and not P of miss. And that's clearly unsatisfiable. If we remove the not P of miss, then what's left is obviously satisfiable, but it's also infinite if we kind of assume that 3 is infinite. And if we remove P of miss, then we can let loss be miss, and what's left is satisfiable by setting P of miss to false. Okay, so we've said the same theorem twice. We're going to say it a third time, okay? And with slightly different notation again. Each one of these is meant to help build your intuition until you get more comfortable with it. So if we say P of A and P of B and P of C and not P of one of them, then the first part, everything except for the negation, kind of corresponds to this infinitely long green bar. And that red square corresponds to the not P of one of them. But note, if we reverse the truth value of the not P of one of them, in other words, if we assert not P of one of them, then that red square would turn green. The problem is that the green area underneath it would turn red, and that would make it unsatisfiable. So it's unsatisfiable as it is. But if we remove the red square, well, that's satisfiable, kind of obviously. If we remove one of the green elements, then we can put the red square, which might not be originally there, but because it's there exists, that means we can choose any one of them, and we can shift it over to where the green square went away, change its truth value, and thus satisfy the overall logical sentence. So that shows that Herbrand logic is not compact.